so much. Since the capability exists in this room. Okay. So what I said last time, is it too loud? Okay, perfect, thank you. You know, I cannot talk louder because then my voice goes high pitch, and it's not very good. When you have all of these points in three-dimensional space, and you want to solve this problem, then first of all, you have to characterize your three-dimensional space by using a coordinate system. Otherwise, if you don't have a coordinate system that is specified, you will not be able to say where those points are, okay? So in a problem like this, I would go, if I were to solve it, I would go and in fact, I will call this Q sub A, all right? Let me try to make this problem easier. A, C, B, B here, okay? And I will erase that for the time being. And let's assume that I want you to solve this problem. I give you everything, and I want you to find the total electric field at point P. And I give you all points, A, B, C, and P. To give, as I said, to give those to you, I have to create a coordinate system. And you can place your coordinate system anywhere you want, and with any orientation you want. But it has to be a coordinate system that is positively defined, all right? So, and I will tell you what that means. You cannot place, from the moment you place X and Y, then Z is specified. And how do you do that? Is the Hen rule, all right, that always goes in a positive direction. So, or mathematically what it means that X, mathematically, with a Hen rule here, if this is my X, and this is my Y, this is my Z. X, Y, Z. If I turn it around, let me see, I cannot turn it around all the dimensions, but if this is my Z, so you specify your Z here, and this is your X, then this is your Y, all right? So it goes X, Y, and Z, or Z, X, Y, all right? It has this kind of rotation, is a counterclockwise. It's a positively defined system. Mathematically, what that means is the following. It means that if I take the cross product of these unit vectors, it gives me that. Do you remember that from the Cartesian coordinate system? Or if I take YZ, gives me X. And if I take ZX, gives me Y. All right, that's what I call a positively defined Cartesian coordinate. Okay, so you place it here, and this is your point of reference. This is where X, Y, and Z are 0. Call it 0. So then I can give you this point, A. So we are deconstructing the problem, all right? That's what I'm doing. So I deconstruct the problem for the time being, so we can solve it. So now I went to the 3 points, and then that's 4. So I can tell you that point A, is a point that has a particular X, a particular Y, and a Z. And for example, for this case, it could be X could be 3, minus 2, 10. All right? I could give you this. And then I could go on and give you B, C, and P in the same way. Okay? Now, if I do this, then I know this vector, I know this vector, I know, let me bring it a little closer, this vector, and then I know this vector. This is vector RA, RB, RC. All right. So far, so good, okay? Now, let's go, and this is, of course, vector R, and I give P, obviously. I have given A, B, C, and P, and this is vector RP. RP. Okay. Now, so I'm done with the definition of the points, but now I need to go back and place the charges here. So I place a charge QA, QB, QC. I place those three charges. And in this problem, and I know how much they are. Let's assume that QA there for the time being that they are identical. 1 coulomb, just for simplicity. Now, I still want you to find the electric field here at P. If I want to find the electric field here, I do not necessarily directly need these vectors, which are the only ones I know. I need this vector, which is RBP. I need a little lower, so the lines do not overlap here. So I need this vector, and I need this vector. Put this a little further. So now I deconstructed the points down to I deconstructed the problem down to the points, and now I'm reconstructing it again. All right. So now I need this vector too. So that was RP. So what I need is this vector, this, and this. Okay? This is RAP. This is RCP. All right. Let's now take the vector RAP. If I were to do here a small, just to isolate only the vector RAP, I don't want to lose the whole picture. This is X, Y, and Z. This is QA. This is RA. This is RP. This is P. And this is what? This is RAP. All right? I know RA, R sub A, I know R sub P. How do I know them? From the points I gave you, A, B, and C. All right? And how can I write this vector? I gave for A, if you remember, for point A, I said it was 2. Was it 2? 2, I remember. No, 3 minus 2 and 10. Okay. How much is vector R sub A? From here, 3A sub X minus 2Y plus 10Z. Is that true? Okay. So now I can find this vector, and I can find this vector. And then let's assume that P, point P, was X 5, Y 6, and 12. All right? Then in that case, R sub P, you remember that, all right? So I will erase this. And then in that case, R sub P would be 5X plus 6Y plus 12Z. Okay? Now, if I know these two vectors, how much is RAP, the vector from here to there with this direction? Remember? RAP is vector RP minus vector RA. Do you remember that? Why is minus and not plus? Think about it, and I will do this here. When you have two vectors, here we have three vectors, and the third one was generated out of the first two. Okay, so if you have two vectors like this, vector RA, vector RB, RP, what is the sum of the two? This. This is RA plus RP. What is this one? This one, this is RA plus RP. This one, this one RP, because that's where it ends, minus RA. Do you remember those? These are from summations and subtractions of vectors. So now, since I know this, do I know RAP? Yes, I subtract these two and I find it. So now what I will do, I will go and do the same thing for this, and for this vector. And then if I do the same thing and I find these vectors, all right, and I have them in vector form, then I can go back to where I had the E. We can go to this one and say total E will be E from QA, E from QB, E from QC. That's my total E at P. All right? And how much is it? All of them have the 1 over 4 pi epsilon naught. And since all of the charges were the same and 1 coulomb, I will leave it here as 1. And then what do I have inside as a summation? From the first one, I have 1 over R AP square. And then this is going to be, in fact, just the unit vector of RAP. And then plus unit vector of RBP square plus unit vector of RCP, and then this one. Okay? Now, do I know these, the denominators? If I know the vectors, do I know their, what are those? RAP is square root amplitude square. I'll leave it like this and then I'll put the square. Equals, do you remember that? Which is, for that will be 3 to the 2nd plus 2 to the 4th plus 10 to the 10. 2 to the 2nd, 10 to the 2nd. All right. And then, because it's in the 2nd power, it's like this. Okay, so I can find from here 9, 4, 100. All right, and that is going to be 13, 113 to the 2nd. And then you do the same thing for all of the other ones. The square, yeah. 113, sorry. The square, sorry. Yes. Thank you. Anything else? I did RA, did I not? I did not subtract. Okay, you got the, sorry, I need to put the right numbers because I was looking at another. RAP is going to be 3 minus 5. So it's going to be, all right? 5 minus 3. 5 minus 3, so it's 2 to the second. 2 to the second plus. And then 6 plus 2, 8. And then 12 minus 10, 2. All right, and that's the second. So that is 4, 64 plus 4. Okay, and that's going to be 70. Is it true? 72. Yes. Good? Thank you. That will be good if you follow what I'm doing here when I don't have my notes, because then sometimes it's very hard to see here from my end. The angle that I have on the board, it's confusing me. All right, so you found this one. You place it here. You will find the same way this one. You will find the same way this one. What is it left there? These 3. How do you calculate those 3? You remember what I said last time? What I said last time is that a unit vector, so I will write it for the unit vector RAP, which only shows the direction of the vector RAP, is nothing else but the vector RAP divided by its amplitude. So the vector RAP, I said it's 2, 5 minus 3, 2, so 2x. And then I have 6 plus 2, 8, y. And then I have 12 minus 10, 2, z. And that is divided by what? 72 to square root of, okay? So now each one of these is a vector. So then you plug in, you find these vectors. So you find these entities, you sum them up, and then you're going to find the E sub p, the field at point P, in this Cartesian coordinate system. All right? Is that clear? That was just as a review of the things that you have seen so far, but that's how we do things. Okay. Now, having done this, I would like you to go to Top Hat. So let's try that. One second. Okay. We'll go to Top Hat from here. Okay, and I have, when you see this pink, this orange, when you see this orange up there, that means that you can review the first set of questions. You can have them always available to you if you want to review them. The other ones are the ones that I have created. So I will start with this one, and I will assign it to you. So I will assign it, and I will give you 5 minutes. All right, and this is what it says. You will read it in front of you as well, and I have assigned it. It gives you the same problem like before. It asks you for a correct solution, and I give it to you that it's C, the correct direction of the force. But now I ask you to identify which angle is going to be generated between this phi sub b right here and this side of the equilateral triangle. So I want you to tell me how much is this angle, and I have given you three choices: 80 degrees, 90, or 100. All right, you have 5 minutes. Work with your team. Huh? What's that? Yes, of course. That's why you are in teams. So work with your team, but enter it separately. And I will tell you when to be ready to stop working. Okay. No, any chances? You mean only there is only one correct question? Okay. Um, just a second. Okay. I will allow you to do this after, for, well, okay. Okay. Okay, you have 1 more minute. So enter your Okay, so time is over. Has anybody entered? No? Okay, do it as, I will have to unassign it, and then you're not going to be able to do it. Okay, so I have to, I unassigned it. So you guys have to, because then I will show you the result. All right, so here. Wait a second. $90. Okay, why is that 90 degrees? Let's try to think about it, all right? These are things that you know how you have done before, but now you need to learn how to use them to solve problems. So all right, the problem was the following. Get my notes here. 3 charges. So you have an equilateral triangle, all right? So all sides are equal. And if all sides are equal, what are the angles? 60. All right, and then I put here a charge 2Q, 2Q. A Q and a minus Q. And then we want to find the force that is exerted from these two, minus Q and 2Q, on this charge, Q. And we said in the first round that why? We said the force between these two, if this force is here, make it a little bigger, longer. If this force is here, longer because we're going to work on this. And then we call this force F1. The force here, this is A, between these two is going to be half of it. Why is that? Because this is 2Q, all right? There is a 2 there, which you're not going to have in the other force. And therefore, the force between these two, which goes like that, is going to be twice in amplitude than the force that is between these two charges. In addition to that, this force is going to have a different direction. This one moves this charge because they are of the same polarity, moves this charge away. This is going to move this charge closer. So it's like that, okay? And then we need to find the sum of these two. So what do we normally do? Something like that. Okay. If this is 60, how much is this? 60. How much is this? 60. All right, let's take this triangle. If I prove to you that this is 90 degrees, then this is 90 degrees. Okay? So let's take this triangle, make it a little bigger just to have better visibility. And let's assume for a moment that this is not 90 degrees. Okay, let's assume that it's not. Then if this is point Q, and this is F1, and this is that point, then I will draw from here the line which is perpendicular to this one. Let me draw this one. And I say, I assume this is not 90. Let me draw one that is 90. This is 60. Okay? How much is we know from this one here, how much is the ratio of, if this were 60, let me just put it differently. This would be 30, all right, if this is 90. If this is 30, how much is this? In fact, I should say, how much is this distance? If this is 30 degrees, then we need to calculate this distance compared to this one. How much is going to be the sine of 30 degrees, which is this distance x divided by this distance y. How much is the sine of 30 degrees? Half. All right? Which, in fact, if this is F1, all right, if this is the amplitude of F1, then that tells me that this one is nothing else but half of F1, which is nothing different than this one. Okay? So that's why this one is 90 degrees. The moment you see that, you do it as a proof, but you need to remember that when you see a triangle that has one angle to be 60 degrees and one of the these sides to be half of that one, then you know that it's a rectangular triangle. But this is the way I would prove it if you had to ask me to prove it for you. Okay? So a little bit of geometry, simple stuff. But that's what in electrostatics we need, that kind of geometrical concepts, because we deal with vectors. All right? So that's number one. Any questions about this problem? Okay. To stay with electrostatics, I will go back to a problem that you did last time. Let me see here. Okay, that is the last one. Do you remember? Oh. No, we don't go to this one. Wait a second. This one. Ah, I'm doing something crazy here. 1 second. Let me see. This one. Okay, perfect. Let me go to this one. Remember this one? The right answer was this one, the first one. What was that problem? This problem was, it gave a charge that was equally distributed on this, in the perimetry of this periphery of this semicircle. Okay, it was here. They get equally distributed. And according to that, it wanted us to find out what was, which was the correct answers. And one of the answers here, can I do that there? You see, one of the answers, the first one, it gives you the solution that the E is going to be only, it will have the X component, and this is not going to be, and EX is not going to be 0. And then it gives you all kinds of other, then it gives you the Z component, X plus Y, and so forth. All right. This is a charge that is distributed like this. And just practically, all right, because this is a conceptual problem, let's assume that I divide this charge into smaller charges, these two, all right, and so forth. You go into, you make it, instead of a continuous distribution, just charges, tiny charges, one next to the other. All right. If I were to do that, then let me erase all of this, but I will use only the first two just to see the. Let me take the first two charges, one piece of a charge here, all right, and one other piece here. This is, I call this Q1 and Q1 here. Both same distance, and this is Y and X. All right. And I am right here. If I'm at this point, how much is going to be the electric field from this charge? Like this. How much is going to be the electric? So this is from E1. How much is going to be Q1 and Q, well, let me call it this, but then Q1 and Q2 are the same, all right? You remember that. And this is going to be E2, and this is E2. And this is going to be the electric field from this one, E1. Since these distances are identical, and these charges are identical, how much is the total field here? 0. So 0 there. Okay. Let me now take these two charges here. They are symmetric with relation to X, all right? And they are anti-symmetric with, I mean, they're symmetric along this axis. So along the X direction. All right. Let's look now at the electric fields. How much is the electric field from this? How much is the electric field from Q1? E1. How much is the electric field from Q2? E2. E1 and E2 have the same amplitude but different directions. But if I were to take each one of those and split them into their X and Y components, how would that be? This one will have one component like this and one component like that. Do you agree? This one will have one component like this and another component like that. So the sum of the two is going to have how many components? Only one, and it's going to be along the X direction. Yes? This is a two-dimensional problem. All right. Okay. It has the form of a semicircle lying in the XY plane of space on it. It's been tested due to charge point of. Okay, charge point on the z-axis. Fine. If this one is only on the x and y, all right, x and y, where x and y, the charges as well as the observation point. Are you going to have a z component in the electric field? Ah, I misread it. Let me read it again. Yes, okay, so it lies, all right. All right, so I took it as a different problem, as a matter of fact. I thought that it said z equals 0. I looked, I cannot see very well. I thought that the a was 0, but it does not matter. If it was at z equals 0, it would be like that. So at z equals a, all right, so that is the problem. It says here that it will have a z component as well, obviously. So in fact, you guys went to the last one, which said that it was going to be an E sub x and an E sub z. An E sub x, but that's what is the difference between the E's? There's the negative x. Okay, well, I apologize for that. I thought in my case that it was along the 0 axis. All right, so, but if it were to be along the z equals 0 plane, if it were to be along on the z equals 0 plane, then it would be like that. Of course, with that being on the z equals a plane, then it makes it different. In any case, that, as I said, is not going to be graded, but this is how I thought. You got it wrong, but obviously you got it right. So that is very good. It's not bad at all. All right, let's try to do the next one. Let's see. Okay, the next one is going to be on electrostatic potential, the next problem, as you can see down here. So we're not going to solve that, but we're going to talk about the electrostatic potential. You have seen what the electrostatic potential is, isn't it? Before, have you seen it? Okay. Yes? The electrostatic potential is another, of course, mathematical entity which we in some ways measure as well. It's not just mathematical, all right, because we have the potentiometers. Have you seen them? So we do have instruments that they can measure the potential of a point in reference to the ground, though. So we measure a difference between two potentials, which is a voltage. So that we can measure. So in some ways, if we know the potential of a reference point, for us is the ground, then we can measure the potential of any other point. So it's not just a mathematical entity, but it is an entity which we have been able to measure, and it is an entity that is directly related to the electric field. Now, you may have seen the potential in two different forms. So electrostatic potential we indicate it by V, and it is a scalar quantity, is nothing else but, in the differential form, is related to E by this. All right? Where this operator, how do we call this? The gradient or the del operator. And this operator operates only on scalar entities and is nothing else but partial derivative with respect to x plus partial derivative with respect to y plus partial derivative with respect to z. Okay? Now, this is a fundamental equation, and as a matter of fact, the reason V is a physical entity and we can measure it is why? Because it's related directly to another physical entity, which is the work. So what does that mean? If we are in an electric field, let's assume that you have charges somewhere and they have created this electric field that looks like that. These are the electric field lines, all right? So if I go here, my electric field is going to look like this. If I go here, it's going to look like this, and so forth. So at every point, if I take the direction of the electric field at every point as tangential, all right, to a line really that goes through this point, then I create the electric field lines. And they can have all kinds of different shapes depending on how the charges are distributed. All right. If I had a charge in this electric field, see. All right, so let's go to this. All right, this problem, it gives a potential function, all right, and then it wants us to find out at what point we have the largest field intensity along this line. All right, so I will assign it to you, and you have 5 minutes. So you can work with your groups. Very good. Okay, so that one is moving well, but you need to it shows up there, isn't it? That's okay, as long as you know how to solve it. I'm very happy about it. All right, so with this problem, since we are moving there, we're moving to the correct, I think we are almost, everybody has responded. I will then suggest that one of your groups tells me which group. Let's see, these are the even numbers, these are the odd numbers. One group there, what's it? 1, 3. No, this is, what group is that? Oh, that's 1, because I see the number 3. Okay, 1, 3, 5, 7, 9, 11. Group 11. So why is this correctly said? Point C is the correct answer. What happens at point C?
It has the steepest slope.
which means that
So the field's going to be the strongest because field relates to potential. It's like the derivative.
exactly. So yes, so it means that at that point, in along the line, the potential varies the fastest. In other words, the derivative that shows the rate of change, all right, along the x direction is going to have its largest value. And that's why the electric field then, because of that, is going to have its largest value at that point. Very good. Okay, any questions so far? So, what did you learn today? That when the potential changes fast, then you have a value in the electric field. When the potential remains constant, then what happens to the electric field? 0. Okay? So, let's try now to erase this for a moment. If we have an equal potential, well, let me put it this way, a different way. If we have a surface where the electric field is 0, and do you know of a surface like that where the tangential electric field on the surface is 0? A perfect conductor, you remember that? On a perfect conductor, let's assume that you have a metallic sphere, and you have electric field everywhere around it. The tangential electric field, the tangential electric field on the surface of this conductor is 0. So what happens to the potential on this conductor on the surface? It has it's the same value everywhere. So whenever you have a metal surface, then you need to remember, and it's a perfect conductor, obviously, you need to remember that the potential on the surface of this conductor is going to be constant, and it's going to have a value, all right? Now, what specifies the value is the rest of the problem, but it's going to have a value V naught, and it's going to be the same everywhere. So let's consider another more practical problem where we have the conductor that we have is a very large plate. All right, a very large plate. Let's assume that if this were to be metallic, like that, okay? And let us assume that we place that in an electric field. Assume that all of this is an electric field, which is, you know why we live in an electric field right now? Because all of your cell phones are operating. Am I right? So every single cell phone is radiating something. Okay, so we have a lot of electric fields. And let's assume that this is metal. What would be the electric field on this surface, the tangential electric field on this surface? We said 0. Did we say that? It's a perfect conductor. So this perfect conductor is going to have the same potential, all right? And let's assume that this conductor is this one. So it's going to have a potential V naught. Now, let's assume that I bring another conductor next to it, like this one. Okay? So this is one conductor, this is another. And I place them like this. So what is going to happen? Each one of them is going to have a constant potential. Do you agree? Okay, so if I go like this, all right, this is going to be V naught, and this is going to be V1. All right? Then let's assume that I bring those very, very close, like very close, this one, but parallel. They remain parallel and I bring them very close. And let us assume that I put a source next to it. Let's assume that this is ground, 0, and then I put a battery. Okay? Do you know what that is? A capacitor, right. And why do I need to know the material we cover? Because then I can calculate the capacitance from this. If this is V, 3 volts, how much is the potential here? 3, because this is ground, 0. And then if I assume that the charge here is this, and here is that, and I assume that the charges are equally distributed, and if I know all of the dimensions of that, this here will allow me to do what? To find the electric field everywhere. Okay? And from the electric field, as you will see later, I can find the capacitance. And this is extremely important. Why is that? Because we cannot design circuits without capacitors. Do you remember that? There are no circuits without capacitors. And the circuits, if you go to integrated circuits, that's how really the capacitors look, but they are tiny, like microns. 1 micron square, 2 microns square. The distance, 1/100th of a micron. And that gives a capacitance, and that's how we have capacitances in here. And that's why it is so important to understand that, because the people who design these circuits, they need to know this material to be able to do it. All right, so it's not just to take you through hell as you try to compute this, it's because it is important to understand it. All right, let's now, since we've talked about that, go to talk about Gauss's law. We'll come back to this later, because we'll be able to calculate both the field and capacitance and so forth. Do you remember when I talked about the potential? Remember that I showed here different lines, all right? I showed these lines. I said these were the electric field lines. Okay, now we are going to introduce another quantity. We call it the electric flux density, and it's going to be related to the electric field. So if this is E, this is an electric field domain. Then D, and let's assume that this is all in free space, all right? Then D, which is the electric flux density, is nothing else but epsilon naught E. And D is called the electric flux density. Okay, why do we call it, what is the meaning of it? Why do we call it a flux? Because what happens to it is it has, other than an amplitude which is different than the amplitude of V by epsilon naught, it has the same direction. So at this point, I can say, I'm not going to call that an electric field. I'm not going to call those electric field lines, but I will call them electric flux lines. All right? So these are the lines of the electric flux. Am I correct? Of course I am, because the direction, these lines show the direction, and the direction remains the same, because we multiply one vector by a scalar, and so the direction does not change. Okay. If we were to go to a more simple problem, a simplistic problem, so instead of this complicated field or flux, we have a charge. We have a charge Q. How are the electric field lines? All right? Radial, as we say. And therefore, what will be the flux density lines? The same, okay? And D here is going to be that. All right, now we have another property, which is called Gauss's law. And according to that, the divergence of D equals with rho V. It says the following. If my charge, let's assume that my charge is inside a sphere. I have this sphere. And let's assume that my charge is evenly distributed inside the sphere. What does that mean? That the total charge Q is going to be the volume integral of rho sub V dV. But I have assumed that rho sub V is the same. All right, so it's going to be what? It's going to be rho sub V times the volume of the sphere. And how much is that? Could you say more, faster? I mean, louder? The volume of the sphere. 4/3 pi what? R what? All right. Where R is going to be this distance, R. And rho sub V is this. Okay. And then, of course, rho sub V here times. All right. That says that if I find myself inside this sphere, and I go to a point in this sphere, and I take inside this sphere the divergence of D, then that is going to be equal to the volume charge density. All right? To the charge at that point inside the sphere. All right. If I were to go from this charge density to calculate Q in this equation, I have to do what? I have to integrate, obviously. All right? And I will have to integrate both sides over a volume. But before I go and do this integration, I wanted to ask you, do you remember what this divergence is, the vector? Del dot. This is a divergence, and you remember this vector, which we call the gradient when it applied on a scalar. We call it the divergence when it applies to a vector. And the divergence on this is nothing else but theta x dx plus theta y dy plus theta z dz. Okay? And the divergence is a scalar. That's why we have that here. So now I go and I integrate both sides of this over the volume of the sphere. dV. And how much is this going to become? This is going to become Q. Okay? There is the divergence theorem. The divergence theorem says that if I integrate over a volume the divergence of a vector, then this is equal. So the divergence theorem says this. This is equal to a surface integral over the closed surface which encloses the volume of this vector d dot ds, this vector which is on the surface of the, all right? So if this is ds, is nothing else but a finitesimal area, and the vector of this surface is this one. Okay, so it's so this is ds, and this is its vector. So ds vector is this one, ds. Okay. So this is called, the first one is called Gauss's law in its differential form. And this one, which is nothing else but Q, is called Gauss's law in its integral form. Okay? Now, let's go back to here. So now we have an electric field because we have an equally distributed charge inside a sphere. The electric field outside is radial, all right? And the values will be, so the value here and the value here will be the same. So it has only one component, which is the radial component, nothing else, the electric field. Therefore, the same lines show what? The flux density directions. And we call these lines the electric flux density lines. If I were to integrate over the surface of the sphere, like here, this integral is going to give me Q, all right? If I want to integrate over a bigger surface, like this, what do I get? Q again. And why is that? Because there is nothing else. The only charge we have is in here, and there is no other charge out here. All right? So again, will give us only Q. So that says that the integral, the closed surface integral, in this particular case, of the vector d, which is the electric flux density, around the charge is equal to the charge. What if, instead of this very nice surface, which is a spherical surface, I go and get a crazy surface that looks like this? And I integrate d over this surface. How much is that integral? Q. So it does not matter anymore because of Gauss's law. It does not matter what kind of surface I integrate around and how far or how close it is to this. As long as it includes the total charge Q, all of these integrals will be the same. Okay? Very good. If I had another, and then we'll have, what time is it? The clock is wrong. Okay, we just need 5 more minutes for the last problem so that I have time to tell you the following. If I get two charges, one plus Q, one minus Q. Here, one charge plus Q, another charge minus Q, identical. What is the field here, the field lines? Okay. What is going to happen if I integrate the divergence d in this problem? It's a problem. When I integrate it around here, around this surface. What am I going to find? Q. What happens if I integrate it here? Negative Q. What happens if I integrate here? 0. Okay, very good. Excellent. Let's do then the last problem, and then we'll move on. Okay. Okay. That shows a charge that is in the southwest, whatever it is, I think. The lowest left corner, Q, and then there is this cube that is oriented like that, the way you see it. And it says that the outward flux of the electric field intensity vector due to this charge through the cube side, which is shaded, you need to find out what is the flux that goes through the surface. Meaning, if that Q is, if this is an imaginary cube and that charge is at this corner, how much of the flux is going to go through the surface, which means that if you integrate D, which is the flux density that is produced by this charge Q, how much of it is going to go through this surface, the shaded, and it shows all the different possibilities. Okay? So you need to identify which one is the correct one. And then you will have about 5 minutes. Okay, so I'll assign it now, and you can go. Did I assign it? Assign. Homework. Why? What happens here? Okay, wait a second. There is a problem, obviously. Assign. What happened? There, okay. All right. 5 minutes from now. I think we are almost there, all right? Let me see. Yep. Okay, ready? I'll unassign it. And here we go. Let me see. Show correct answer. And this is it. All right, that's the correct answer. The majority of you were correct. And why was it 1 over 24? Who like group 8? Group 8? There. So why was it 24? Why was it not 8, whatever else they had, 2, 6? Mm-hmm. 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 Why is it only 3? Why do we only have a flux flowing from 3 and not from all of them? So what happens on the other faces where we don't have any flux going through? The field is the D lines, the flux lines are parallel. They don't cross them, all right? Because if you have flux lines that go like that, and you try to integrate along this direction, there is nothing that crosses this surface, all right? So that's why they don't cross these other surfaces because they are parallel. Okay, very good. The last thing we like to do today is to bring your attention, there are only a few more minutes, but in the notes that I gave you for today, I have 2 examples where we're trying to calculate the charge density. The charge is distributed. They give us the charge density, but we try using the charge density to calculate the total charge. In one case, in the example, and I would like you to go through these examples and try to solve them yourselves as well. The one case is something like that. It shows in my notes, and say there is a square plate that is on the XY plane, and they give the size of the plane, of the square plate. And on this square plate, there is a charge density that varies with Y. This is on the XY plane, all right? It's a square plate, but the charge density is a function of Y. And then I want you to find the total charge on the plate. It's just an integral, practically. So it's practicing with integrals. And the other is it gives a thick spherical shell. So the dark blue inside is like air. The charge is only in the light blue, and then outside is air. And it gives the shell by the 2 radii, 2 centimeters and 3 centimeters, and also gives the charge density as a function of the radius in that shell, and asks you to find the total Q. So that's another example in spherical coordinates. Okay, so there are 2, just to find the Q, because the moment you know the Q, then you know the integral on any surface that encloses it. And so if you know the total Q. So practically by knowing the total Q, you know that on every surface that encloses this spherical shell. All right, so it's an example, and please go through it to calculate it. Any other questions from today's lecture? Okay, around 6 p.m. I'm going to have a survey for you. So give me any feedback, what you would like to see more, what you do not like from the lecture, or what you like to see, whatever. Okay? Please do them. Thank you.
So, for the one where it was the triangle, was it roughly 90 degrees or was it exactly 90?
Exactly 90.
Oh, okay. Because I did a little bit differently.
Okay?
Where, so for this one it's 2, and I used a unit vector.
Okay.
And for this one, this simplifies to 1, and I used a unit vector going that way. And then I added them up, and then I took the inverse tangent.
Maybe is it in somewhere do you do that? Did you do an approximation because it's supposed to be 90?
Okay.
Yeah.
So you're supposed to do an approximation?
No, maybe that somewhere.
Because like that's the exact answer. I just wanted to make sure that I did it correctly, you know?
Could you send me a?
Okay.
What do you indicate by that?
So this is just a unit vector.
That you're
And this is also a unit vector.
Okay. On the XY.
Exactly. And I added them up.
Why do you not send it to me and I will check it out to tell you? Okay.
Professor, can I ask a real quick question? I didn't understand the parallel part.
Okay. This one, so there are, if you were to enclose this cube with a spheric, with a cubical surface, you will have 8 like those.
Right.
All right, 8 like those. And so in each one in this one, you only have 1/8 of the total, all right, flux. And then since it's 1/8 and only goes out from these 3 surfaces.
Okay, it goes out from only top, this side,
Yes.
and the side on the back.
Yes,
Why?
because here is parallel. The flux lines on the other 3 surfaces are parallel.
Okay, so flux doesn't go to
It does not. According to that, if your D is parallel to the surface, then this gives 0. All right. So it's only coming out of these 3.
Okay, thank you.
You're welcome.
Hi,
Hi.
I'm on the wait list. Yeah.
Okay. No, you should be. I will. You should stay because I'm going to open the number for the class up to 100. So you should be able to make it.
Okay.
All right. I will just. I told already that on Friday to the registrar's office, but I will remind them again.
Okay. Thank you.
So you just stay in the class.
Okay. So next time I go to class, will I have a group?
No, yeah, you should be. What is your name?
Long Yuan.
I will check. It shows all on Canvas. It should show everyone who is on a waiting list, and I will place you in a team. So check in your Canvas. All right. Let me see. As a matter of fact, here, Canvas.
Canvas. Check Canvas.
Okay. Let me see people. Pages people. Okay, so I have every student here I have placed in a group. So, thank you. It is
It's people. Isn't
in the
people?
people, yeah, if I go to everyone,
Oh, okay.
2 invitations haven't been accepted.
I could.
Here, what is this? Pending. What is this pending? What's your name? No, you're not that
Long Yuan.
one. Yeah, no.
Oh, my last name is C. It's over there.
No, right. So you are part of it.
You am part of it?
Yeah. Student waitlisted, but you are in the team. And to see, say what team you are in. So
Because
you should be able, if you look at people, to see your team group. Do you see the groups? Go to, let me see. What do you see? Syllabus pages, grades, assignments, conclusions, modules, conferences, collaboration, chat. Let me see what is the group. One moment. Home. If I go to student view and I look